Hello friends, welcome to my lecture on languages and grammars. We will have 3 lectures on this topic. So, let us begin with the first lecture on this topic. See, in our daily life we come across 2 types of languages. One is the spoken language and then other one is the formal language. The spoken language is the one which you see in villages or in cities. That language does not follow any rule. So, it is very complicated, it does not have any grammar or a set of rules which it follows. So, the other language which is the formal language, that language follows certain set of rules, it is scientifically defined. So, that language is the one which we are going to discuss. A language is called formal if it is provided with a mathematically rigorous representation of its alphabet of symbols and formation rules, specifying which strings of symbols count as well formed. Formal languages are studied in linguistics and computer science. Formal language is a set of words, that is finite strings of symbols taken from the alphabet over which the language is defined. A grammar is a set of rules to define a valid sentence in any language. It does not describe the meaning of the sentences or what can be done with them in whatever context, but only their form. Now, let us define an alphabet. An alphabet is defined as a finite non-empty set of elements or symbols. For example, sigma equal to the set containing 0 1 or sigma the set containing 0 1 2 3 and so on up to 9 numbers, and sigma equal to A, B, C and so on up to Z, the uppercase letters of English alphabet, and sigma can also be taken as the set consisting of small case letters of the English alphabet A, B, C and so on up to Z. Sigma is the representation of for the alphabet. Now, let us define a string. A string or word, a string or word on an alphabet sigma is defined as a finite sequence of symbols in sigma. Say for example, you take sigma to be the set consisting of the letters A and B, then you can take the string or the word U as A B A B. It is consisting of the letters A and B which are there in the set sigma. Okay. You can also take another example where we are taking A B B. Okay. So, it is a word or it is a string which is defined over sigma. So, U and B are both a finite sequence of symbols in sigma. Now, A to the power I, okay, A to the power I is used to denote a sequence of IAs, okay, that is A square we can write for A cube we can write for AAA. Okay. So, if there are IAs, okay, then IAs can be written as A to the power I. Now, if you have U equal to AABB, then we can write it as A cube B square. Okay. The length of a string U, the length of a string U is denoted by this symbol. Okay. Norm of U you can call is the number of, it is the number of symbols in the string. So, for example, in U there are 5 symbols A, B, B, there are 5 symbols. So, norm of U will be equal to 5 here. Okay. Now, here we are taking U to be A, B, A, B. Okay. So, norm of U will be equal to 4. There are 4 symbols A, B, A, B. Okay. And in B we have A cube B square. Okay. That is A is occurring 3 times A and B is occurring 2 times V. Okay. So, norm of B will be equal to 5. Okay. The empty sequence of letters is denoted by lambda or it is also denoted by epsilon. It is considered to be a string on sigma and we call it as empty string. Okay. The norm of lambda is defined as 0. So, the empty sequence of letters is denoted by lambda or epsilon and its norm is defined, length is defined as to be equal to 0. Now, if sigma is an alphabet, then sigma to the power k is defined as the set of strings of length k, each of whose symbols is in sigma. Okay. So, if sigma is equal to 0 1, then sigma 1 is equal to 0 1, sigma 2 will be consisting of the strings of length 2 each made up from the elements of sigma. So, 0 1 are the elements of sigma. So, we will have 0 0, 0 1, 1 0, 1 1. In sigma cube we will have strings of length 3, okay, made up from the elements 0 and 1. So, we can have 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 1 0, 1 0 1, 1 0 0, 1 1 1. You can see each of them is has length 3. Okay. So, they are elements of sigma cube. Now, let us define closure, we also call it cleanest star. So, let sigma be an alphabet, then the cleanest star sigma star is defined as the set of all strings including lambda, the empty string. So, lambda is also there in sigma star. Okay. So, sigma star is defined as the set of all strings including lambda, the empty string over the alphabet sigma. So, if sigma is equal to the set consisting of 0 and 1, then sigma naught, okay, sigma naught is equal to the set consisting of lambda only, lambda is the empty string, sigma 1 is equal to sigma, which is the set consisting of 0 1. Sigma 2 consists of elements each one of length 2 and made up from the elements of sigma. So, 0 0, 0 1, 1 0, 1 1. Sigma cube is the set made up from the elements 0 and 1 having length 3 each. So, 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 1 0, 1 0 1, 1 0 0, 1 1 1. Okay. Sigma star. Now, sigma star is the union of all these sigma to the power I, where I varies from 0 to infinity. Sigma naught, union sigma 1, union sigma 2, union sigma 3 and so on. Okay. So, when you consider the union of these sets sigma naught, sigma 1, sigma 2, sigma 3, sigma 4 and so on, you get sigma star. So, sigma star is consisting of lambda, okay, lambda 0 1, then 0 0, then 0 1, 1 0, 1 1 and then the elements containing strings of length 3 each. Okay. So, 0 0 0, 0 0 1, 0 1 0, 0 1 1, then 1 1 0 and so on. Okay. So, that is sigma star. Now, let us define sigma plus. Sigma plus is defined as the set of all non-empty strings. Okay. So, that means we have to exclude empty string from sigma star to arrive at sigma plus. So, sigma plus is equal to sigma star minus lambda. Lambda we have seen, lambda is this, that lambda is sigma naught, sigma naught equal to lambda. So, we remove the empty string lambda from the set sigma star to get the set of non-empty strings, that is sigma plus. Now, let us define operations on strings. So, let u and b be two strings in sigma star, then concatenation of u and b written as u b is the string obtained by writing down the letters of b to the right end of u. For example, u equal to a b a b and b equal to a b b, then u b will be equal to, so that is a b is u, then we write the string of b to the right end of u. Okay. So, b is a b b. Okay. So, u b will be equal to a b b a b b. Okay. So, that is how we define the concatenation of the two strings u and b. Now, properties, there are certain properties which concatenation follows. So, the concatenation follows certain properties. There the properties are, if u is a string, then u to the power n equal to u n number of times. Okay. And as a special case, we can say that u naught is equal to lambda. Now, it also follows the associative law. If u b w belong to sigma, then concatenation of v and w, when we consider its concatenation with u is same as concatenation of u and b with concatenation of w. So, the identity element is also there, the empty string lambda is an identity element for concatenation, because lambda u equal to u lambda equal to u for all u in sigma. Now, it follows the right cancellation law. Whenever u b w belong to sigma, then w u equal to w b implies u equal to b, and it also follows left cancellation. Whenever u b w belong to sigma, then u w equal to v w implies u equal to b, and if u and b belong to sigma, then length of u b, this is length of u b, it is equal to sum of lengths of u and b. The length of concatenation of the strings, you can define this equality. It says that the length of concatenation of the strings is equal to sum of the individual lengths. Okay. So, whenever we consider the length of the concatenation of u and b, what we get is it is equal to the sum of the lengths of the individual strings u and b. Now, substrings are subwords. A word w is called a substring or subword of w if we can find b 1 and b 2 such that w is equal to b 1 u b 2. If b 1 equal to lambda, in particular if b 1 equal to lambda, then u is defined as an initial segment. Okay. Note that lambda is a subword of w. Why? Because w is equal to lambda lambda w. Okay. So, lambda is always a subword of w, because we can find b 1 and b 2 where we can take b 1 equal to lambda, b 2 equal to w, such that w equal to b 1 lambda b 2, where b 1 is lambda. Okay. Let us take b 1 equal to lambda and b 2 equal to w. Then w we can write as b 1 u b 2. Okay. So, this is equal to b 1 is lambda, u is we are taking as b, u we are taking as lambda, and then b 2 is equal to w. Okay. So, w is equal to lambda lambda w. So, lambda is always a subword of each word w. Now, also w is a subword of w. Okay. Why? Because we can take b 1 and b 2 both to be equal to lambda. Okay. W is equal to, it can be written as lambda w lambda. Okay. So, lambda is always a subword of w. Now, let us take w equal to a b c d and let us see what are subwords of w. Okay. So, first subword is lambda, because we have seen lambda is always subword of w. Okay. Then a is a subword of w. How a is a subword of w? See, you can take b 1 equal to lambda. Okay. I can write w equal to lambda a and b c d. Okay. So, I am taking here b 1 equal to lambda and b 2 equal to b c d. Okay. So, then I am able to write lambda equal to w equal to lambda a b c d. So, here b 1 is lambda and b 2 is b c d. So, I am able to write w equal to b 1 u v 2. So, a is a subword of w. Similarly, you can write b as a subword of w, c is a subword of w, d is a subword of w. Now, ac, how ac is a subword of w? So, w equal to, I can write lambda a b and then I take c 2 as c d. I take b 2 equal to c d. Okay. So, here I am taking b 1 equal to lambda and b 2 equal to c d. Okay. So, a b is a subword of w. Similarly, b c is a subword of w. We can write w equal to a b c d. Okay. So, where I am taking b 1 equal to a and b 2 equal to d. So, I am able to write w equal to lambda w equal to b 1 u v 2. Okay. b 1 is a, b 2 is d. So, b c is a subword of w. Similarly, c d is also a subword of w. Now, a b c is a subword of w. Why? Because I can write w equal to lambda a b c and then d. Okay. So, I am taking b 1 equal to lambda and b 2 equal to d. Okay. So, a b c is a subword of w. Similarly, b c d is a subword of w. Here I will take b 1 equal to a and b 2 equal to lambda. Okay. And a b c is a subword of w, because every word W is a subword of itself. So, A B C D is a subword of W. Now, initial segments, let us see what are the initial segments here. Initial segment is lambda, lambda is always the initial segment. Why? Because I can write see let us look at the definition of initial segment. W equal to B1 U B2, okay. Then we say that U is a subword of W. If B1 equal to lambda, okay, B1 equal to lambda, then U is an initial segment of W. So, I can say that lambda is an initial segment of W, because I can write W equal to lambda lambda W, okay. I can write W equal to, so here this B1 is lambda, okay, U2 is lambda, okay, and B2 I am taking as W. So, B1 when B1 is lambda, then this U is called an initial segment. So, lambda will be an initial segment of W. Now, similarly A B, okay, how A B are initial segments? W can be written as lambda A, and then B2 I will take as B C D, okay. So, take B1 equal to lambda and B2 equal to B C D, then A will be an initial segment of W, okay. Now, let us look at the initial segments, okay, of the word W, okay. So, lambda is an initial segment of W, because I can write W equal to W equal to lambda lambda W, okay. So, here B1 is lambda, okay. So, if B1 is lambda, then this is U, this is U, okay. U is called initial segment of W. So, lambda will be called an initial segment of W. Now, A will be initial segment of W, because I can write W equal to lambda A and then B C D, okay. B2 I will take as B C D and B1 is lambda. So, I am able to write W as B1 union B2, okay. So, A is an initial segment of W, okay. Then AB is an initial segment of W. I can write W equal to lambda AB and then CD. So, I will take B1 equal to lambda and B2 equal to CD, and similarly ABC will be initial segment of lambda. I will take W equal to lambda ABC and then I will take B2 equal to D, okay. And ABCD, okay, is always initial segment of W, because then I will write W equal to lambda ABCD lambda. So, I will take B1 equal to lambda and B2 equal to lambda. So, the initial segments of W are lambda, A, AB, ABC, ABCD. Now, AC or ACD, okay, let us look at AC or ACD. AC or ACD are not subwords of W, although their letters belong to W. You can see their letters A, B, C, D, they belong to W, but they see W is ABCD, okay, W is ABCD. So, the letters A, C, A, C, D belong to the W, but AC is not a subword of W. Why it is not a subword of W? Because it will be called a subword of W only when you have to you can find B1 and B2 such that W equal to B1 U B2, but W is equal to ABCD. So, if I want to check whether AC is a subword of W or not, then I need to find B1 and B2 such that W equal to B1 U B2, okay. So, AC, if I, this is my U, okay. Now, I cannot find B1 and B2 such that I am able to get ABCD, okay, because B lies between A and C, okay. In the word W we have ABCD. So, B lies between A and C. So, B cannot be inserted here between A and C. B1 is to the left of the letter A and B2 is to the right of the letter C. So, we can never get ABCD. We will never get any B1 and B2 such that W equal to B1 AC B2. So, AC is not a subword of W. Similarly, ACD is also not a subword of W. We cannot find B1 B2 such that W equal to B1 ACD B2. Now, let us consider prefix and suffix. Let X and Y be two words over an alphabet sigma, okay. So, let x by be 2 words over an alphabet sigma, then x is called equal to y, written as x equal to y if x and y both have the same length and they have same symbols at the same positions. X will be called a prefix of y if I can find a word z over sigma such that x z equal to y. Okay. For example, suppose x is equal to I n, okay, and y equal to I n d I n, y equal to I n d I n. Okay. Then this is my x, okay. Then there exists a word z, okay, such that y is equal to x z. So, z I will take as d I a n. Okay. So, in this case where x is I n, y is I n d I a n, okay, we are able to find a word z which is d I a n such that y is equal to x z. So, x is a prefix of y. Okay. Now, if you look at this example, x equal to can, y equal to scan, okay, then x is not a prefix of y, because we are not able to find any z such that y equal to x z, okay, y equal to x z, x is can. Okay. So, x is can and z is some word, okay, from the alphabet sigma. Okay. So, z cannot be found such that you get scan, okay, because s occurs to the left of can. Okay. So, we will not be able to get any z such that scan is equal to can z. Okay. So, there does not exist any z which can give you can z equal to scan. So, x is not a prefix of y. Similarly, you can see y is not a prefix of x. If y is to be a prefix of x, then x should be equal to y z for some z, some word z, okay, and x is equal to can and y equal to scan, okay, scan. So, you cannot get can, okay, you cannot get any z such that scan z is equal to can. So, y is also not a prefix of x. Now, x is called a proper prefix of y. We can now define proper prefix. Proper prefix of y if x is not equal to lambda and x is not equal to y. Also, x is a prefix of y. So, x will be called a proper prefix of y if x is not equal to lambda, x is not equal to y, and x is a prefix of y. Now, since x equal to lambda x, lambda is always a prefix of any word including self, because I can write lambda equal to lambda lambda. Okay. So, lambda is always a prefix of any word that follows from here, and it is also a prefix of itself. Now, further x equal to x lambda. So, x is always a prefix of itself. Okay. These are simple things. Now, let us define similarly we can define suffix and proper suffix. Okay. If a word x will be called, x is called a suffix of y if there exists a word z such that y equal to zx, okay, then x will be called a suffix of y. Okay. And we can also define proper suffix. Proper suffix means okay, x is called a proper suffix of y if x is not equal to lambda, x is not equal to y, okay, and x is a suffix of y. X is a suffix of y. Okay. So, like we have seen here that lambda is always a prefix of any word x, we can also say that x equal to x lambda. Okay. So, lambda is a suffix of any word x, and also lambda equal to lambda lambda. Okay. So, lambda is a suffix of itself. Okay. And also x equal to lambda x. Okay. X equal to lambda x. So, x is a suffix of itself. Okay. Now, here we have an example. So, let us say take x equal to happy, okay, x equal to happy and by equal to unhappy, okay, unhappy, then x is a suffix of by, or we can check that it is a proper suffix of by, because x is not equal to lambda, x is not equal to by, and x is a suffix of y. Now, let us define reversal of a string. The reversal of a string is obtained by flipping over the last symbol. Okay. For example, if u is equal to x y z, then u r means reversal of u r will be equal to z y x, u r equal to z y x, u r is the reversal of u. What is a palindrome? A palindrome over an alphabet sigma is a string that reads the same both forwards and backwards. For example, if u equal to a b b a, okay, then it is a palindrome, because u r is also equal to a b b a. Okay. A b b a. Okay. So, u is same as u r. So, it is a palindrome. Now, if S is equal to a a b, okay, if the set S, let us consider the set S is equal to a a b, then the Kleene star S star, Kleene star we have earlier defined. So, here the sigma set is the set S, okay, it is consisting of A and B. So, S star is union I equal to 0 to infinity S I. Okay. Now, S naught is the set containing lambda, S1 is the set containing length elements of length 1. Okay. So, we have B here S square, because if you remember sigma k was the set of all strings of length k. Okay. So, here sigma is S. So, S1 means a string of length 1, and there are two elements here, one is B, the other one is A. B has length 1, A has length 2. So, only B will be there in S1. S2 can have all elements of length 2. Okay. So, A will be there, and from B we can have BB. So, BB will be there. Okay. S cube, okay, S cube will have elements of length 3, strings of length 3. So, we can from A and B we have to form strings of length 3. So, we can have AAB, okay, we can also have BAA, this one, and we can have BBB. Okay. Nothing else is possible here. Okay. So, that is S cube. And S4, from S4 we have to in S4 we have to have strings of length 4. So, from A we can write AA, it is a string of length 4, and then from B, A and B we can write AA, BB. Okay. We can also write BB, AA. Okay. So, AA, BB, BB, AA, and we can then write BB, BB. Okay. B can be repeated 4 times. So, BB, BB. So, these 4 elements will be there in S4. And now, S star is the union of all such SIs, okay, where I runs from 0 to infinity. So, S star is this much, okay, this set. Now, if S is ABC, then S naught is lambda, S1 is the set of strings of length 1. So, ABC all are there, lambda star is then lambda ABC, and then length S2 will contain elements made up from of length 2 made up from ABC. So, we will have AA, AB, AC, BB, BA, BC, CC, CA, CB, okay, this will be S2, okay, and then similarly we can write S3. So, AA, AB, AC, BB, BA, BC, CC, CA, CB, these are elements belonging to S2, and then we will have elements of length 3 each made up from ABC. Okay. Now, let us take sigma equal to 0 1, alphabet sigma we take as 0 1, then let us also take P equal to the set containing 0 1, 0 1 1, 1 0 1, and Q as the set containing 1 1. then PQ. Okay. The set PQ is defined as now we write the elements of P, okay, and to right of P we write the element from Q. Okay. So, let us take the element from P to be 0 1, okay, this one. Then PQ will give us to the right of 0 1 we write the elements from Q. So, 1, okay, this is one element, then 0 1 with 1 1. So, 0 1 1 1. Okay. So, we get two elements, okay, when we pick up an element 0 1 from P and take all elements from Q, and then take the second element from P 0 1 1, and then adjoin this to the elements of Q. So, we write the elements of Q to the right of 0 1 1. So, we have 0 1 1 1, 0 1 1 1 1, okay, and then 1 0 1, that is the third element of P. So, if we adjoin the element 1 0 1 of P to the elements of Q. So, 1 0 1, then 1, and then 1 0 1, and then 1 1. Okay. So, these are the elements of PQ, and similarly we write the elements of Q. We pick up an element of Q and then write to the right of the element of Q all the elements of P. So, when we have 1 here, okay, Q we take the element 1 of Q and then write the all the elements of P to the right of 1. So, 0 1, that is one element, then 1 0 1 1, then 1 1 0 1. Okay. Now, we have adjusted all elements of P. Now, let us take the second element of Q 1 1, okay, and then we write to the right of 1 1 all elements of P. So, 1 1 0 1, 1 1 0 1 1, and then 1 1 1 0 1. Okay. So, these are the elements of QP. Now, language, any collection L of words from an alphabet sigma that is any subset of sigma star is called a language over sigma. Sigma star we have already defined, sigma star equal to union sigma k, k equal to 0 to infinity. Okay. So, you take any subset of sigma star, it defines a language. Okay. It is a language. Now, a string, so any collection of words from an alphabet is a language. Now, a string in a language is called a sentence of the language. So, if sigma is a b, then sigma star we can write sigma naught is lambda, sigma 1 is sigma, that is a b, sigma 2 is we have earlier seen a b, b a, b b, that is sigma 2, and then similarly we can write sigma 3 and so on. So, then union of all these sets, that is sigma star. So, lambda a b, a b, b b, b a, then a b and so on, that is sigma star. Now, let us take L 1 to be this set a b square, okay. Then L 1 is a subset of sigma star, you can see L 1 is a subset of sigma star. So, L 1 defines a language, and you can describe this language in words. L 1 consists of all words which begin with an A followed by one or more B's. So, we can describe this subset of sigma star which defines a language. This language consists of all words which begin with an A followed by one or more B's, and then another set you can take L 2 of sigma star. It is containing elements a to the power m, b to the power n, where m is a positive integer, n is a positive integer. So, this language L 2 again describes a language. So, L 2 consists of all words beginning with one or more a's followed by one or more b's. So, here a's and b's, number of a's and b's can be different. Okay. So, that is the language L 2, and then the language L 3. It consists of a to the power m, b to the power m, where m is a positive integer. So, L 3 consists of all words beginning with one or more a's followed by the same number of b's, and L to the power 4 L 4 is b m a b n. So, here a lies in the middle, okay, and on the left of a we have b's, okay, one or more b's, on the right of A also we have one or more B's. So, L4 consists of all words with exactly one A, which is neither the first nor the last letter of the word, that is there is one or more B's before and after A. Okay. Now, we have seen that language is a set. Okay. Language is a set. So, all the operations like union, intersection and difference hold true for languages. Okay. So, complement of a language L, complement of a language L is defined as L complement equal to sigma star minus L. Okay. And inverse of language L is defined as L inverse equal to W R, W belongs to L. So, W R means reversal of W. So, in L inverse all the elements that belong to L, we take their reversal. Okay. Those elements belong to L inverse. Now, we have concatenation of L1 and L2. Okay. Concatenation of the set L1 and L2 is given by L1 L2. It consists of the strings UB, where U belongs to L1 and B belongs to L2. The union of L1 and L2 denoted by L1 union L2 is the set containing W, where W belongs to L1 or W belongs to L2. Now, let us define power of a language. Okay. Suppose L is a language, then L naught consists of empty string lambda. Okay. L1 is equal to L, Lm plus 1 is defined as Lm L. Okay. That is concatenation of Lm with L. Okay. Where m is greater than 0. For example, suppose L is equal to ABC, L is consisting of two elements A, B and C. Okay. Over this set sigma. Okay. Right. So, then L naught is the set containing lambda, L1 is equal to L. So, it is consisting of A, B and C. L2 is LL. Okay. L2 is by this definition it is LL. Okay. So, concatenation of L with L. Okay. Concatenation of L with L, L is equal to ABC, A, B and C. So, L square will be LL. So, we write the elements of L to the right of the elements of L. So, AB we write, and then to the right of this AB we write AB. Okay. So, that is one thing. Then AB to the right of AB we write the another element C. Okay. Then we can also have C to the right of C, we can write AB. Okay. That is L square, and then we can also have CC. Okay. So, AB, ABC, CAB and then CC. These are the elements of L square. Okay. And then we have L cube. L cube is L square L. Okay. L square is AB, ABC, then we have CAB, then we have CC. Okay. And we have L. L is containing A, B and C. Okay. So, concatenation of L square with L. Okay. So, we have AB, okay, AB, that is one element, then AB and then C. Okay. So, corresponding to AB we have two elements AB, C, and then corresponding to ABC again we have two elements ABC and then ABC. CAB gives CAB, AB and CABC, and then CC gives CCAB and then CCC. Okay. So, we have altogether 2 into 4, that is 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, negative power of a language is not defined. Do not consider this L inverse which we have defined here as the negative power of L. It is just a notation. It is the set which consists of the reversal of the words of W. It is not the inverse as we usually understand. Now, let us consider A to be the set ABC. Let us find L star. Okay. So, L star, when L is equal to B square, L equal to AB, C equal to ABC. L star, if you take then so if we take L equal to B square, okay, then L star consists of lambda and then all elements made up from B square. So, B square, B square, B square, B square, B square, B square and so on. Okay. So, that means it is lambda B square, lambda B square, B to the power 4, B to the power 6, then B to the power 8 and so on. So, it consists of the empty string lambda and all even integral powers of B, even positive integral powers of B, okay, that is L star for the case B square, and L equal to A B. When you take L equal to A B, then L star equal to lambda, then A B, B A, B B, okay, and then we will have A, okay, A, then we have A B, then we can have B A, we can have B B and so on. Okay. So, these will be the elements of length 3. Okay. We can take A 3 times, we can take 2 A's, okay, and we can take 1 B, we can take 1 A, we can also take A B B, okay, that will also be an element. Okay. A B B, we can then take single B and 2 A's, okay, single B and 2 A's, B A, okay, and then we will have B B A and B B B. So, those elements will be there of length 3 and so on we can have. So, L star will consist of lambda and all elements made up from A and B. Now, C equal to A B C cube. So, let us find L star here. So, L star will be this is L equal to A B C. So, L equal to L star here will be lambda, then we will have A B C cube and then we will have A B A C cube, okay. We also have A here, okay, A, then A B, then A C cube, then B B A B C cube, okay, then C A C B C C cube and so on. Okay. Sorry, C A C cube A, C cube B and then C cube C cube. Okay. So, all these elements belong to L star when L is equal to A B C cube. That is all in this lecture. Thank you very much for your attention.